And yes, the recording has started. Now, it's 8:31. We are already late by 1 minute. Now, what did we talk about yesterday? Yesterday, we talked about fork. We talked about fork. We talked about how to create a clone of a process. And that's pretty much it. That's all that fork does. It creates a clone of a process. A clone in every aspect, except for the process ID. So the child process is a different process ID than its parent, and it continues to execute the same code, starting from the instruction right after the return of the fork system call. Now, of course, creating a clone doesn't mean that you have created, that you're running a new program. You are still running the same code. Now, in order to replace the code of the clone process, or of any process, if you will, with the code of another program on the hard drive, for that, we have the exec family of system calls. The exec family has many variants, you will see, exec VE, exec VP, and so on, but they always start with exec. Now, the exec VE system call loads a new program into a process's memory. So in order to call it, you need to have a running process. And the moment that you call exec, or rather the moment that it returns from the system call, the code of that process, its memory space, its variables, all of them disappear, they are discarded, they are thrown to trash, and they are replaced by the code, variables, etc. of another program on the hard drive. So basically you start with fork, you create a clone, and then that clone is replaced with another program by calling exec. During this operation, the old program is discarded and the processes stack, data, heap, so everything, basically, everything, are replaced by those of the new program. So the only thing that remains is basically the process ID. So it continues to have the same process ID, but everything else, it is replaced. Now, the most frequent use, of course, of exec VE is in the child produced by fork. So fork to create a clone, and then by calling exec in order to replace it with a new program. So now various library functions, all with names beginning with exec, are layered on top of exec VE, on top of the exec VE system call. Each of them have a different interface, but they all pretty much do the same thing. Let's look at them. So very simply, if you just type man exec, you will see the entire suite of the exec family. So we can see that there is exec L, exec LP, exec LE, exec V, exec VP, exec VPE, and so on and so on. So all of them, and the only difference is basically the way in which they admit their parameters. But behind the scenes, they're all doing pretty much the same thing. As it says right here, the exec family of function replaces a current process image with a new process image. The functions described in this manual page are frontends for exec VE, and so on and so on. So you have all the details, technical details, within this manual page. Now, we are more interested in the rough guidelines concerning this system call. So how do you call it? How does it work? Well, of course, you need the Unix standard header file. So exec VE. It has 1, 2, 3 arguments, and interestingly, never returns on success. Never returns on success, which makes sense. Which makes sense. If exec VE is successful, well, that means the process that called exec VE no longer exists. All of its code is replaced by the code of another program. So you will never see what exec VE returns if it is successful. That's interesting. Never returns on success. So if you actually receive something as a return value from exec VE, that means it's failed. That means it failed to replace the running process with the code of another program. Never returns on success. Very interesting. Now we have 3 parameters: path name, the arguments, environmental parameters. So basically, what are we trying to do? We are trying to run a program from the hard drive in such a way that it would replace the current process. So we need to tell the system call which program we want to run, with which arguments, with which environmental parameters. So we have to give it the path name of the program that we want to execute, naturally. We have to give it the arguments with which we want to execute that program. And of course, if there are any eventual possible optional environmental parameters, we can also provide them too. Okay, now the path name contains the path name of the new program to be loaded into the process's memory. Well, okay. argv is the argv specifies the command line arguments to be passed to the new program, and of course argv0 must correspond to the command name, you know, as it is always in C. And of course the final argument, envp, specifies the environment list for the new program. Now you can also of course leave it empty, if you will, or you can also fill it up. But if you do decide to fill it up, it must correspond to the environ array of the new program. So it is a null terminated list of pointers to character strings in the form name equals value. So for instance, if I type env right here, I see all of the environmental parameters defined for this shell. So you need to give all of these, and you see how they are defined like this, as name equals value. For instance, user equals Erhan, or what is the shell? Or shell equals bimbash. So you need to give it a list, a null terminated list of such strings, if you want to, of course. So you can execute a new program and tell it specifically what to use as a path, what to use as the username, what to use as, I don't know, as the library path, and so on and so on, if you want to. In general, the envp third argument is not really that frequently used, to be honest. Now, since it replaces the program that called it, as we said, a successful exec.ve never returns. So we are expecting it not to return. We never need to check the return value of exec.ve, so it will always be -1. The very fact that it returns, so you don't even have to look at the value. If it returns with no matter what, that means it failed. The very fact that it returned informs us that an error occurred. So what kind of errors can happen with exec? So we can have e-access, erno set as e-access. What does it mean? It means that the path name argument doesn't refer to a regular file, the file doesn't have execute permissions, or one of the directory components is not searchable. Okay, so we cannot access it, basically. Eno end, the file referred to by the path name doesn't exist. Well, also possible. Eno exec, the file referred to by path name is marked as being executable, but it is not in a recognizable executable format. Or etext busy, the file referred to by the path name is open for writing by another process. So we cannot just execute it while somebody is writing into it. Or e2big, the total space required by the argument list and environmental list exceeds the allowed maximum. So these are just some of the errors that can take place when you call exec. So should you be checking for the return value of exec? Absolutely. But the exact value doesn't matter. It doesn't matter if it returns -1 or -10 or -1 million. The fact that it returns is sufficient for informing us that it has failed. So what do you do then? Well, the usual stuff. You check the value of erno and proceed accordingly. Example. Let's look at our example. So here we have our main method, our main function, argc, argv, as usual. We are receiving a lot of arguments from the command line. We have also received the environmental parameters. So we have two environmental parameters, greet equals salut and bye equals adieu. Okay. So how are we supposed to use it? If the user gives us the incorrect number of command line arguments. So in that case, we are printing the usage information. This is how you should be using it. So the name of the program, and then we need a path name. So what to execute? Okay. So we get the so argv1. We get the name of the no, we don't get it. We are just searching it, str search. So we are searching for the character / in there in order to get the name of the program that we want to execute. We are preparing in the array argvec, the command line arguments of the program to execute. So the first one must be the name of the program that we want to execute. So we're placing it in argvec 0. And then in argvec 1, 2, 3, we are placing the argument. So we are going to run the program of which the path name was provided as a command line argument. And in positions 1 to 3, we are placing hello world and goodbye. Okay, and then we simply call execve by telling it to run that program with these arguments in argvec and these environmental parameters in the mvec. So basically with 2 parameters there too. And that's it. And if by any chance the program ever reaches this line, well, that means execve has returned, and that means execve has failed. So normally, this program should never reach this row, because as soon as you call execve and it returns, that means this program no longer exists. You have an entirely new program, the program in the path name, that is running now in its place. That's the whole idea. Any questions about this? Here, for instance, we are printing. So this is a program that we have attempted to run, for instance, the program env-args. And here is what it is printing. It is printing its environmental variables, and it prints whatever we have given it. So we have given it these command line arguments, hello world and goodbye. So the command line arguments are there. It is printing its environmental variables by accessing them through the environ global variable right here. And indeed, the variables that we passed it are there. So yes, it is working. And also please note that we are once again using the exit success in order to denote a successful execution. Yep. Well, I'm guessing you do not have any questions at the moment. Okay. It's too early for questions, I guess. Now let's look at the rest of this library. So we have exec-le, exec-lp, exec-vp, exec-v, exec-l. So mostly we have either a p or a vl or an e. So what do these combinations denote exactly? So let's see. For instance, in exec-ve, we accept the path name. So directly the path of the program that we want to execute. Okay. If it also has V or L, depending on if it has V or L, we are expecting, in the case of V, an array containing the command line arguments. Okay. If, on the other hand, there is a L in the name, that means it is expecting a list containing the command line arguments. If you see the E in the name, such as in exec-ve, that means we are also providing the environmental parameters as part of the call. If, however, E is missing, such as in the case of exec-v, there is no E in this case, and you can see that it only admits 2 parameters. So we are not giving it any environmental variables, and instead, the new program is supposed to use the default environmental parameters coming from the caller's environmental parameters. So it is basically inheriting, in a way, those parameters. That's pretty much it. If by any chance you also see a P in the name, well, in that case, that means search for the file in the directories specified by path. So we are only giving it the name of the program to execute, not the full path. And we are telling it to use the default path of the system in order to look for it. So depending on which combination of these letters you use, exec-ve will behave slightly differently in the way that it looks for that program to execute, in the way that it passes its parameters to it, but behind the scenes, it's still doing the same thing. Run that program, replace the current process. That's it. Any questions about the exec library?
Sir, so it search for, I'm Doruk.
Yes, Mr. Doruk.
So it search for the file you said with the exec L, I guess.
No, exec L. Now V and L. Now with P. Now, for instance, let's look at exec V right here. Exec V. Now with exec V, so that means it has no P in the name. That means it will look directly for that path name. So you have to give it directly the path name, the full path or relative path, but directly the path to the file that you want to execute. Doğrudan onun yolunu vermen lazım. If on the other hand you use P, so if on the other hand you use a version of exec with P in the name, such as exec LP, exec VP, in that case, it is expecting just the file name. So you only give it the file name, such as ls. I want to execute ls, but where is ls? Well, in that case, you're telling it to look to the path, environmental variable, to find the file name that you have given it to execute. And what is the path? For instance, the path on my system is, what is the path? It's right here. Path. Az önce buradaydı, gördüm seni ya. Here it is. So if I simply call exec LP and I tell it to run ls, it will look to all of these folders to find ls. But if I use a version that doesn't have P, such as exec L, exec V, exec LE, I have to give it exactly the location where ls is located. So /bin/ls or /sbin/ls. That's the difference. Any other questions?
Thank you.
You're welcome. Okay. And now let's get to your favorite topic. What happens to signals when you use exec? So what happens, for instance, if, I don't know, the process that called to exec had blocked certain signals? Do they continue to be blocked after the return of exec? Does the new process, or rather the new program that gets executed after exec, does it inherit anything from the process that executed exec? How does it work? Let's look at it. During an exec, the text, so the code of the existing process, is discarded. So that is for certain. The entire code of the process that called exec, çöpe gitti, it's trash. Okay. However, this text may include signal handlers. Now, these handlers are going to disappear. The handler functions, they existed in the code of the process just before calling exec. So now they are gone. So there is no way of executing those handlers. They are gone. They have been replaced by other code. So because the handlers disappear, the kernel automatically, you don't have to do it, the kernel resets the dispositions of all handled signals to sigdfl. So whatever signals the process that called exec was trying to catch and handle, all of those signals are now automatically set to the default disposition. So whatever is the default behavior when being delivered a sigint, sigterm, or whatever, that is what will happen. That is what will be in place when the new program starts. Now, of course, the new program that replaces the old program, it can establish new handlers. It is free to do that. But when it starts executing, that's how it starts. By having set to default disposition, to default behavior, all the signals for which the previous process had established handlers. Are we clear about this? Is this understood? Okay. What about all the other signals? What other signals? The signals for which the process that called exec had not established any handlers. Well, all the other signals are left unchanged. So whatever was blocked was blocked. Whatever is ignored is still ignored. Whatever is free to be delivered is free to be delivered. Signals, so what are we supposed to do? What is the guidelines on how to act, how to behave when calling exec in terms of signals? Now, signals should not be blocked or ignored across an exec of an arbitrary program. Now, Mr. Anil says, if the old program didn't have a handler, how the kernel, if old program didn't have a handler, would kernel still do that? Well, Mr. Anil, that's what it says here. The disposition of all other signals are left unchanged. So If there was no handler for it, the kernel is not touching it. So if, for instance, the process that called exec, let's say it blocked sig_int, then after exec, in the new program, the new process, it continues to be blocked. Let's say that it had ignored, it had set to ignore, I don't know, sig_term example. It continues to be ignored in the new process after calling exec. But whatever signal for which you had a handler in the previous process, in the new one, that handler is now cancelled, and instead the default disposition is in place. That's the idea. So the dispositions of all other signals for which you didn't have handlers in the original process, they are left unchanged. Now, how should we behave? What are the recommended guidelines when developing such programs? In general, if you intend to call exec, try not to block or ignore any signals, basically. The only exception to this, it is acceptable to block or ignore signals only when executing a program that we have written, or one with known behavior with respect to signals. So what does this mean? It means that if you have written such a program that will call fork and then exec, or directly exec in order to start a new program, you shouldn't mess with the signals, because maybe, just maybe, the new program that you're going to run after exec makes assumptions about the behaviors in place towards certain signals. And you might ruin those assumptions by giving it something different. Örneğin şöyle söyleyeyim arkadaşlar. Çünkü biraz ince bir nokta. Madem exec çağırdıktan sonra yeni sürece eski sürecin sinyaller için aldığı önlemler miras kalıyor, handler'lar hariç. Bunu yapmamakta yarar var. Yani varsayılan davranışları değiştirmemekte yarar var sinyaller için. İşte belli bir sinyal by default varsayılan davranış yok sayılması mı? Örneğin sig_user1, sig_user2 bırak öyle kalsın. Neden? Çünkü o yeni başlayan sürecin hangi varsayımlarla, sinyaller hakkında hangi varsayımlarla hareket ettiğini bilmeyebiliriz ki genelde bilmiyoruz. Belki sen onu blokluyorsun. Atıyorum Ctrl+C'yi blokladın mesela ve haydi başlattın exec'le yeni süreci. İyi de o yeni süreç sanıyor ki Ctrl+C bloklanmayı ve ona göre davranıyor. Ama sen blokladın. Ya da bütün program yapısını alt üst edeceksin. O yüzden genelde eğer exec yapacaksan sinyallerle fazla oynanmakta yarar var. Hani varsayılan ayarları neyse o şekilde bırakmakta yarar var. Tabii bunun tek istisnası eğer exec ile çalıştıracağınız programı da siz kendiniz yazdıysanız, dolayısıyla biliyorsunuz nasıl davranacağını. O zaman tamam. Durum bu. That's pretty much it. Example of fork and exec. These slides are available at Moodle, so you can also follow them from there. So what does this program do? It spawns a child process running a new program. Now, program is the name of the program to run. The path will be searched for the program. So we are going to search the path. Arglist is a null terminated list of character strings to be passed into the program's argument list. Returns the process ID of the spawn process. Okay, so let's look at the main. So in the main method, here we have the list of command line arguments to pass. So we have ls, root. So we are going to list the root directory terminated with a null. As we said, a null terminated list of command line arguments. Okay, that's nice. And then we call spawn and we tell it to run the command ls with this argument list. So how does spawn work? Let's look at spawn. So the name of the program and the list of command line arguments. So we call fork. Now from this point on, we have two processes, the child and the parent. Now, if the child process is different than 0, so that means this is a parent process. And the parent process, it does what? It simply returns the process ID of the child process. Else, now this means we are in the child process. Now we call exec VP. So with P, we give it the name of the program, which means that it is going to search in the path in order to find this program. And we are giving it the list of command line arguments. Now, if it manages to reach this point right after exec VP, that means exec failed. So fprintf to standard error, an error occurred in execvp, or you can use perror or whatever, and then just exit, abort, etc. So normally, this program should never reach this point after execvp. Any questions about this example? Okay, in that case, I'll be back in just 30 seconds. I'm very sorry. Arkadaşlar kusura bakmayın, ev hali, kargocular gidiyor geliyor sürekli. Kapıyı da açacak kimse olmayınca böyle. Okay. Any questions in the meantime about exec? Now, system. Now we have already seen system. We saw that system is a library function, not a system call, despite the name. It's a library function that is used in order to execute a new program. And we had said that you shouldn't use it because it is not safe and it is not very efficient. Why it is not efficient? Because it starts two processes instead of one. It starts a shell process, the shell, and gives it the command to execute. So basically it starts one process for the shell, and the shell starts the process that we want to execute. So two processes instead of one. Not very efficient, and plus, if your program uses the system library function, that means it is also vulnerable to the same flaws as the system, as the shell that is run by system. Now, let's look at how we can implement system on our own by using fork, exec, wait, and exit, because those are the only ingredients that we need in order to implement it. And let's see how things work behind the scenes. Now, of course, system has disadvantages, but it also has advantages too. I mean, otherwise it wouldn't exist. Now, what are the principal advantages? Well, basically it's simplicity. So you don't have to go through all the fork and exec and signal handling and errors and so on and so on. You just call system, give it the program to execute, and that's it. You don't have to worry about signal handling, error handling, etc., etc. So, as we said, inefficiency and two processes. Now, if efficiency or speed is a requirement, and of course, if security is a requirement, it should always be a requirement. Of course, it is preferable to use explicitly fork and exec. But how? Now, first look at how we can use system, and then we will look how we can use the alternatives in place of system. Here in this program, well, we have our main method. We have a buffer of size max cmd len, and then we have an infinite for loop. Now, in this infinite for loop, we basically are expecting the user to enter a command. So basically, this is a shell in a way. Bir nevi arkadaşlar bir şey gibi kabuk şeklinde bizden komutlar bekliyor. Komut gir, çalıştırayım diyor. Tamam. O yüzden sonsuz bir döngü var. That's why we have an infinite loop. It's a shell that is continuously expecting us to enter a command to execute. So how does it work? Now, it says constantly command. So it is expecting us to enter something, basically. It flushes out the standard output, and here it expects the command from the standard input. It gives us a buffer of size max cmd len, and with fgets expects us to enter the command. Now, as soon as it receives the command, it takes it in str and gives it to system to execute it. As simple as that. Now, that command, whether it is properly typed or not, it is given to system. Now, if it is properly typed, ls something something, it will be executed. We will see the output and so on. And system will give us the status. So whether it was executed successfully or not. Here we print the output. Now, as you will remember, there were different kinds of outputs in order to denote whether the system function failed or whether the command has failed. Now, that was during the previous sessions. So if it returns -1, that means, well, system has failed. Now, otherwise, we are trying to collect the value with which the command has returned. So we are using the w if exited and w exit status macros, and we apply it to the status value returned by system, just like we saw yesterday. So to see if it has returned 127, well, that means it probably couldn't invoke the shell. Otherwise, so if it is neither -1 nor 127, well, that means it has actually returned the status of the process that just got executed. So, and then it returns to the beginning of the for loop to expect the next command to be input by the user. So a simple shell, a very simple shell based on the system library function. Any questions about this? For instance, can you tell me why it is calling fflush here between the printf and the fgets? Bu sefer de ben sorayım.
Clears the buffer of printf.
Why? I mean, yes, fflush clears the buffer, but why does it clean the buffer right there at that point? What happens if we don't call it? If we don't clear the buffer, what could happen?
Well, maybe it gives some buffer overflow error or something like else.
Mr. Furkan, I mean, imagine that you didn't call fflush and you immediately call fgets. Now, fgets will try to read from where? From standard input. Now, right here, we're flushing std out. So basically, if you do not flush it, the standard output, the next time that you try to printf whatever system has returned, you will also receive that stuff in the buffer as well. So it will complicate your output. So before you print what the system library function has returned, you want the buffer to be completely empty. Otherwise, you will receive just before the string all the other stuff that was in the buffer as well. So that might confuse the person using this program. So that is it's good practice to clean the buffer. Anyway, so here we have a sample run. So we are executing it. So here we have the shell. So it is expecting a command. We enter the command who am I, which returns the name of the user. So it's the user mtk. So the system has returned status 0. So the command has been successful. The child is exited to status 0. Then it is expecting command again. We enter ls pipe grep xyz. So as you can see, the entire command is interpreted by the shell. So you do not have to worry about redirections, pipes, etc. No problem whatsoever. All of them are handled by the system library function. So that is the advantage, the main advantage of the system library function. You do not have to implement these things on your own. Pipes, redirections, büyüktür, küçüktür işaretleri, etc., etc. So that is, well, that is definitely a significant advantage. Okay. Now let's look at implementing on our own. Now to implement system, we need to use fork to create a child process. And then we need to use execl, or one of the functions in the exec family, to implement a command similar to the one that you see right here. So we need, if we try to exactly replicate the shell, we need, of course, to start the shell. And of course, we need to give it the command line arguments. So the first one will be naturally the name of the shell and the command later on to execute. And of course, in order to collect the status of the child process after it terminates, we will need to use one of the family of wait functions, and preferably wait process ID to wait specifically for the process ID of the child process. Let's look at it. So here we have the our own implementation of the system library function. So it receives the command. Okay. And what does it do with the command? So status, we are calling fork. We now have two processes. If fork has returned -1, we immediately return -1. We have failed to fork. We have failed to create the shell process. Otherwise, case 0. So that means we are in the child process. Well, in that case, we call execl. So the child will be replaced by the shell running the command. And if it reaches this point, well, that means execl has failed, and it returns 127. So basically, the shell failed to start. And by default, so that means by default, we are in the parent process. In that case, we wait for the child to terminate by giving it the process ID of the child. Now, if it fails with -1, that means wait failed. We return -1. This function has failed. Otherwise, we simply return the status of the child process. And there you go, the system library function in all its glory. Now, at this point, of course, you might ask, hocam, niye wait değil? Now, if you use wait, that would not suffice. Why? Because wait waits for any child, for the first child that terminates, for the first child of this process that terminates. So it could accidentally collect the status of some other child process created by this process. Whereas with wait PID, we are specifically waiting for the child process that we just created. Oh, sorry. Any questions about the implementation of system? Kimse soru sormuyor. Bu konular kolay herhalde. Peki. İnşallah ödevde de böyle düşünürsünüz. Now, how to treat signals inside system. Now, as you have just seen, I mean, executing a command is not really that complicated. Call system or otherwise just fork and exec, and that's it. But what happens with the signals? What happens with the signal? That's what complicates the situation. Now, what adds complexity to the implementation of system is the correct treatment with signals. Now, the first signal to consider is sick child. What was the signal about? This was the signal that the kernel sends automatically when the child process terminates to the parent process. So how do you handle it in this case? Now, the first signal to consider is sick child. Suppose that the program calling system is also directly creating children and has established a handler for sick child that performs its own wait. In this situation, when a sick child signal is generated by the termination of the child created by system, it is possible that the signal handler of the main program will be invoked and collect the child's status before system has a chance to call wait bit. Bayram mübarek olsun. Ne diyor burada? Now, a program is running this function. We are giving it a command. We are forking, and we are executing to run that command. Okay. Now, this is a new process, execl. it replaces the child process with the process of the shell. Now, when this terminates, here we are trying to collect the status of that child. But what if the program that is calling system is also listening to the sick child signal? Well, in that case, the moment that this child process terminates, a sick child signal will be automatically sent to this process. And instead of running this wait PID, it will catch that signal and maybe run some other wait. I mean, the entire problem is that this program can have other children as well, besides the children that it is creating in order to run these commands. And what if it is also trying to catch sick child coming from those other children processes, while at the same time trying to wait for the child process that is running this command? Haydi şimdi çıkışın içinden çıkabiliyorsan. Arkadaşlar problemi anlatabildim mi? Bu süreç sistemi çalıştırıyor. Sistem fonksiyonu. Bu gördüğümüz fonksiyonu. Bu fonksiyon bir çocuk süreç yaratıyor. Execl ile shell'i çalıştırıyor falan filan. Sonuç olarak bir çocuk süreç var. Ve o çocuk sürecinin sonucunu beklemek istiyor. Ama ya diyor bu sistemi çağıran süreç başka çocukları da varsa bu sürecin ve o süreçlerden gelebilecek olan sick child'ı da yakalamaya çalışıyorsa o zaman bundan gelen sick child'ı da yakalamış olacak. Bu wait bit hiçbir zaman çalışmayacak belki de. Çünkü oradaki sick child yakalanıp oradan bir wait yapacak. O zaman burası takılacak kalacak böyle. Sonsuza kadar. Çıkış içinden çıkabiliyorsa. Therefore, system must block the delivery of sick child while it is executing. Bu şekilde işin içinden çıkıyorsun. Therefore, in order to avoid a deadlock such as this one, the system function must block, and it does block, the delivery of the sick child signal while it is executing. Now, the other signals, besides sick child, to consider are those generated by the terminal interrupt, such as Control-C, that lead to sigint and sigquit, depending on which control combination you use. And sigint and sigquit should be ignored in the calling process while the command is being executed. Otherwise, that Control-C might terminate the program that is running even the shell. Be careful on that. So the general idea on how to treat signals, you should block sick child and ignore sigint and sigquit in the calling process, the process that executed signal. And this is what we have here. Let's look at it. So the proper way to handle, the proper way to execute system now with signal handling. Now pay attention to how simple it was before the signals entered this, and now pay attention to what is happening. So what do we have to do? We need to block sick child, and we need to ignore sigint and sigquit. Why? In order not to have the issue with the waits with sick child, that's why we're blocking it. And in order not to terminate the calling process due to a Control-C or a control backslash, etc. So in case sigint or sigquit is sent. So we want those signals to be handled by the shell. Okay, so here we have the block mask, the original mask. We have sig actions, 1, 2, 3, 4 of them. We have the process ID, status, the saved errno, and so on. So, number one, if the command that has been provided to us is null, well, in that case, there isn't really much to do. We immediately return, what? The call to system, whether it is equal to 0, 0. Now, what does this mean exactly here? Can you figure it out?
I didn't understand, actually.
Okay. Who did understand it? So basically what it does is, if this system function has been called with no command, so if it has been called with null, a null pointer, it says in that case, execute system and check, execute it with a command of 2 points. and check its return value. If it returns 0 successfully, so if it calls the shell with those 2 points to execute, well, in that case, that means a shell exists. It executed, it returned 0, system, and a shell exists. If it returns even -1 in this case, well, that means there is no shell. So in order to be able to execute system, you need to give the command to a shell. So, and for that, you need to have a shell on that system. So basically, it is checking whether the shell exists and whether it is basically available. Anyway, that's not really that important. Let's look at the signals. That's the important part. This is not really that portable either. Now, we need to block sick child. So first, we have this block mask. So we initialize it to an empty set. So initially, none of the signals are set inside it. We add sick child. So only the sick child signal is set in this mask. And we call sick proc mask with the flag sick block. And with this block mask, in order to block it. And we make a backup of the original mask. A backup of the signal's original mask before blocking sick child. Okay, so why are we taking a backup? Because at the end of the system, at the end of the system function, we are going to put that mask back in its place. Now we need to ignore sigint and sigquit. So we set the handler to ignore the flag to 0. For which signals? Well, we first empty the mask, and then we call sig action with this SA ignore for sig int and for sig quit originally. And we take the backups in both cases. Okay, so we're going to put those backups back after we are done. Nice, so we have ignored them. Then we call switch. Inside it we have fork. If fork returns -1, well, that means fork failed. We could not create a clone, so we break. There is nothing to do. If it returns 0, well, that means we are in the child process. So what does the child do? Now, the child first sets the handler. Now, be careful at this point. We want default disposition. For what? Let's pay attention. Now, remember that sigint and sigquit are now blocked. Okay. Now, since they were blocked in the parent process, in the child process, they are also blocked. So that means when you execute exec, they will also continue to be blocked. Is that something that we want? No. No, we don't. Now, that's why we're setting them to default disposition. So the handler is at default, the flag is at 0. Now the sig action mask is initially set to the empty set. Now, in case it says, in case the handler, the original handler, the one before blocking, was set to something other than ignore, well, in that case, bring it back to the default disposition right now, before we call exec, so that the new process that we're going to execute, so the shell that would execute the new command, will have the default disposition for those two signals. So the blocked status of sigint and sigquit will not be transferred to the shell that we are about to execute. So in this case, we are calling sigproc mask, and we are setting the mask to the original mask, and then we call execl. Now, if it by any chance it returns and it reaches this point, well, basically that means that exec has failed, and it has failed very miserably. If on the other hand, we are default, so switch returns something other than -1 and 0, well, that means we're in the parent process. And in the parent process, what do we do? Well, very simply, we have to wait for the child that we just created. Okay, so we call wait pit, but we call it properly, so in a while loop. So as long as it returns due to an interrupt, we call it again. So wait pit for the child. If it returns -1, and if that -1 is due to an interrupt, well, in that case, we need to wait again. But if it is due to something other than an interrupt, well, in that case, you wait again. You keep on waiting. Now, this should be here. Niye kaymış bunlar hepsi böyle ya? And after you are done, after you're out of the switch, of course, you need to set all the masks to their original versions. So the saved error is placed in it, it's put back in its place. The masks of which you took the backups, they are placed back. So once again, the sick child is unblocked, and SIGINT and SIGQUIT, they return to their original dispositions, and then you return the status. That's a lot of work. That's a lot of work for system. Well, this is how complicated things get when you deal with the signals. I know you don't like them. I don't like them either, but they are there, and somebody needs to handle them. Long story short, 1, block sick child when you use system, so that there won't be any issues when you call wait bit, any handlers outside this function that might catch sick child and prevent you from returning from wait bit. 2, ignore SIGINT and SIGQUIT so that the shell will catch them, and in case it receives SIGINT and SIGQUIT, they will not terminate the original process. Now, that brings us to the topic of daemons. Now, this is an easy topic. I mean, we will be approaching the topic of daemons in more detail towards the end of the semester, but just a few points about them. How is a daemon process different than a regular process? Now, a daemon process is just like a regular process. They started the same way with fork and exec or system or whatever, but their difference with respect to standard processes, non-daemon processes, is that 1, they are usually very long-lived. So they have a very long lifetime. They usually start when the system boots up, and they continue until the system shuts down. So they are expected to run for a very long time. 2, they run in the background and they have no controlling terminal. They are not associated with any terminal. You cannot just type in something and send it as input to a daemon. It doesn't work that way. They don't have any terminals associated with them. So that means you cannot, by accident, send any control Cs or whatever to these processes. So they are protected somehow in a way. And 3, by convention, well, in general, let's say, but traditionally, they have names starting with the letter D or ending with the letter D. For instance, let's look at my system. Oh, sorry, hangi klavyedeyiz? Türkçe klavyedeyiz. So, for instance, here, what do we see? If we go to the top, we will see any daemons here. Up here, snap D. The name ends with a D, started by root. This is a daemon. Process, anything else? Up power D, another daemon. Rootkit daemon. TeamViewer D, daemon. System D, daemon. Demonized login for the keyring. What else? ibus kill daemon. dbus daemons. Now, in these cases, as you see, they do not start with a D, but well, in this case, it starts with a D. It also has the name daemon in it. The dconf service, etc., etc. Now, how do you create a daemon? Now, to become a daemon, let's look at the steps. You perform a fork. Bu arada yetişebileceğiz bunları yapmaya. Yetişebileceğiz gibi. To become a daemon, the program performs the following steps. Of course, you need to perform a fork, after which the parent exits and the child continues. Okay. The child process calls set SID. Now, in this case, the issue is that we need to disassociate ourselves from the calling terminal. So normally, a process that starts after fork, it still has a controlling terminal. It is associated with a terminal from which you can send it input. You can send it control Cs, control Hs, control Ds in order to stop it or interrupt it. Now we need to disassociate this process from those terminals. And there is a certain amount of steps that we need to carry out. And As we have 5 slides explaining those steps, I do not want to rush it at the moment since we are already at 9:26, and I will leave this to the beginning of the next week's session. So we'll dedicate 10 minutes then in order to explain it in detail, because even though it is not really of that much importance, I still would like to explain it properly when the time comes. So don't worry about it. We will talk about the daemons next week. And in the meantime, of course, you will have probably a new homework this week, now on processes and on waiting processes. So, yeah. Yeah, that's all from me for now. And we will put a mark. We will put a mark at this point, and we will continue next week from slide 38. What I recommend to you is to read up whatever you can find on processes, process creation, process termination, and signal handling on your book, and try to understand it as best as you can. And whatever you cannot understand, note them down, send me emails, and if everything goes all right, I will see you next week, Wednesday at 8:30.
Have a good day, sir.
Thank you. Sağ olun arkadaşlar. Hepinize iyi
Have a nice day,
dersler.
sir.
Thank you. See you next week. İyi günler arkadaşlar.
İyi günler hocam.
İyi günler beyler.